teaching a course in calculus remotely, and this is first semester, so I'm going over some of the things that we require. In particular, I'm going over which was Rolle's theorem and what they call the mean value theorem, and then there's some theorems that we use in addition. So I'll go over that as we go through this. But basically, I'm trying to start from scratch as much as I can, and to build up through what we call the mean value theorem and Rolle's theorem, which simply says on a two-dimensional surface, if you have a curve and you have one point x, let's call it a to b, then if you have a function above that at some point along between a and b, you're going to find some point c such that the tangent line will be the slope of the tangent line will be 0, or be equal to what we call a secant line. So the slope of a secant line. Let me go over it. But before we even start, I'll start up here. Let me go up here. Yeah, starting from here, basically I'm just going over what a continuous line is. So we need to define what it is to be continuous. Rigorously, we define it with a limit, and we see if the value at a particular x value is the same from left to right, then we say, okay, it's continuous. But what it means actually is like right here. So if I have a dot here and here, notice how I trace this out without lifting my cursor, my stylus. Well, then we call that continuous, you see. But then we have another measurement. We call it the differentiability, which is really kind of a smoothness. You can see how this is kind of smooth here. Sort of a degree of smoothness, which means at any time I put a tangent line, we can find the slope of that. Or tangent line here, or tangent line here, right? These are different m slopes. It changes, you see. And that's really why we need the calculus, because, you know, if you wanted to find the area of the area like this, or let's say a physics problem, let's say this is speed and distance. So if I'm going, let's say we got time. Yeah, so if I have 1, 2, and I'm traveling at, let's say 60 miles an hour. And then we want to know how far we go in 2 hours. In this case, it's represented by the area, right? So we would have traveled 120 miles. As really the area of this would be how much distance traveled. But what happens if we have a distance traveled looks like this? It's not so easy now to find the area, nor is it to find out exactly, you know, because it's changing. So anytime you have this kind of changing, where the slope is changing, we're going to need calculus. Okay, so the second example, that was the first example. The second example is a kind of a way you would build a fractal. It's sort of kind of like a snowflake, that we start with something kind of, well, we'll start with this, for example. Yeah, and then like a crystal, we'll put a kink in it here, and a kink in it here, and a kink, and a kink, you see? Then each one of these will have their own kink, and it goes forever and ever. It becomes like a fractal, becoming more and more complicated. A fractal is something that's, wherever you look, if you zoom in enough, it's going to be spiky again. So the problem with spiky is that we can't find the level of smoothness or the slope of it. We can't find it when x is here underneath a spike, under this peak. Because if you tried to put a tangent line through there, right, you could put one like this, and another one like this. Like, there's an infinite number I can put in. That's why, in order to do what we need to do, we have to have a curve, or a graph that's continuous and differentiable. And remember, that's a degree of smoothness. If it's too kinky, there's nothing, we can't actually find the slope, right? And one thing that's kind of interesting is that a fractal, for example, is continuous everywhere from A to B, like here from A to B, but it's not smooth anywhere. It's kind of even a hard concept to just picture. As you zoom in and zoom in, everything that you think is flat is the beginning of another spike. So a fractal is continuous everywhere, but differentiable nowhere. Isn't that odd? But anyway, that it's actually stuck in a dimension and a half. Like it's, I mean, in a fractional dimension, but we'll go from there. So really, I'm just trying to show that if we have some kind of curve, and let's say in this case, it's like this, so that there's some value c such that there's going to be a tangent line here whose slope, and we can call that the derivative evaluated at c. That's how we do slope. That's how we do the derivative. Now let me get this. Okay. Okay, so what we do is the slope of this tangent line is going to be like this. See, you can see in this case the slope is going to be equal to f of c. Why do you bring him here? And then there's a c. So we see there exists a c such that the slope of that tangent line, if we're right here, there's another value here, let's say x of 1. Well, the slope is not 0. So if this point and this point are the same, in this case both, if I call this guy right here a and I call this b, right? And notice that the y function, the y amount at that point are both zeros, then we can use what we call Rolle's theorem. So let's see if I can show you what I mean there. And let me go here. Okay, so let me scroll up. So with Rolle's theorem, it says if you have a function, which we just spoke about, this is the function, and let it be continuous, see? So we'll call it, let it be continuous. On a closed interval, that means this right here between a and b, including the endpoints, see? And it's differential, I mean it's sufficiently smooth that we can find a slope on there. On the open set of this guy, does not include the endpoints. And if, remember, a and b have the same value, in the case of this drawing up here, the value, or the y value is 0. You could have it something like this, just so, oops. So you have a graph like this, right? And as long as this value is equal to this value here, that's where f of a would equal f of b, see? If that's the condition, that's this. Then we can use Rolle's theorem. If it's that case, then this arrow here in mathematics, we call it, means then. Then there are at least one number, c, and this guy here, these colons, means such that, that's what that means, such, that's an H. Such that there's a C in AB, such that the derivative of that curve evaluated at C will give me, there exists a C prime that equals 0. Or that if you were right out the line for that tangent line, the slope would be 0, okay? Now, let's see if we can kind of work ourselves through the Rolle's theorem proof, right? There's 3 cases, I think, that we should consider. One is if we have a function like this, so that it's what we call it's a uniform distribution, if you will. And so from a to b, there always has this y value of d, right? This is d. That's where that meets. So in this case, we can see that f of a equals d, which is equals f of b, so it's the same value, where d is just a constant, you see? Good. So so if f of a, so f of a equals 0 and f of b equals 0, so that any c between a and b, there exists an f of c equals 0. Now in this case, it doesn't have to be 0, but it has to be the same. F of a has to be equal to f of b to use Rolle's theorem. So, but in this case, you can see that if we're uniform, all values are here. Any value here is a c value. It will work. Because any one of those evaluated there, right? You can see that the tangent line of this thing, by any over the open interval AB, all values can act as a c. And in case you can see that, of course, there is going to be a something like this, right? It does exist because the whole function, the top of it is the easiest of all. That slope is 0 at any value of x between a and b, or any value of c between a and b. Now that's the easiest. Now case 2 is when we have something like where c is underneath the hump, so to speak. So we would know that there must be a tangent line somewhere that is equal to 0. So what we do is that first what we're going to say that f of x is going to be greater than d. So in the case of f of x is greater than d, and then so since f of c is greater than d, then we say f of c prime is equal to 0. So let's go over that again. So suppose in case 2 that f of x, so every value of f of x here, right, is going to be less than d. So d we can say is the local maximum, right, from here to here. Let's go from here to here. So this is going to be a local maximum as we go up from here to here. There's the local maximum, see? And so since f of c is greater than d, so then f of c must be equal to 0. So suppose that f of x is greater than d for all x element of the open domain between a and b. And since the way it's set up, that f of c is the highest point. That's an f of c. It's not very good. Let me put it right here. This is going to be an f of c. F of c, it still doesn't look good. So if I take f prime, so there's an f of c right here. That's the only time. Otherwise, all other values of f of x are less than that point, meaning that's a local maximum. So we can see in this case that as you can see what happens to your tangent line. See, there it's positive, and over here the tangent line has a negative slope. That can only be as if they have somewhere at some point where the slope f prime of c is equal to 0. And case 3 would be something like upside down values, so that what we have is something like the opposite, where we have a minimum like this. Yeah, so that every value of x is less than the value d instead of more than the value d. So for some x element between a and b, so that f of c is less than d because it's the lowest point, such that f of c is prime. And since it's smooth, down here, then we have a tangent line, right? Right here the tangent line is negative, see? Here the tangent line is 0, and here the tangent line is positive. So necessarily, at some point, there must be a c such that the slope of the tangent line is equal to 0, right? So we know, let's go up here. We know that f has a minimum or a maximum for some c value, see it? For some c value that's an element between a and b. Here's the lower one. Now I went all through that to show now a more general case. It's called the mean value theorem. This is more general because I am not requiring that f of a, we are not requiring that f of a, here, let me put it like this. In this case, it's more general, so we are not requiring that f of a equals f of b. It's not necessarily required. It could, maybe if it does, well, we can just use Rolle's theorem. If it doesn't, we'll use the mean value theorem, and this is how it is. So if f of x looks something like this, see, when we graph it out, right, and then we have a secant line. Let's see if I can make that a little bit bigger. Oh, here, okay, so if I had a secant line like this, see, and so because this is a and this is f of a, see it, and this is b, and here's f of b. So they're not the same value, but there's a brilliant, I thought it looks kind of a brilliant way to prove it. And like most things that we do in mathematics, if we have a function that's, we feel it or seem to be complicated in solving, then oftentimes we try to convert it into something similar to what we already know how to solve. So what I'm going to convert this guy, you see this, I'm going to convert this guy here. Let's go here. I'm going to convert this curve. What I'm going to do is I know that there's a tangent line here, and this is the secant line down here, and this is the tangent line. So what the mean value theorem says that there's going to be some value of c, right? There's going to be some value of c such that the slope f prime, let's call this f prime of c, will equal, and when we talk about the secant line, we'll just call it y prime, right? So that these two slopes are equal. I mean, there's a value of c such that the slope right here is the same as the slope right here. You get it? So the mean value, if again we need it to be continuous, we need it on a closed interval between a and b. That's the endpoints. And differentiable means smoothness between a and b. And this arrow means then in mathematics. And this e in reverse means there exists a number c that's an element between a and b such that f prime of c is equal to the slope. Now, the slope of the secant line. So we're saying that this guy is simply an average slope. So that's the slope from the slope of the secant line is going to be equal to the slope of the tangent line. There is going to be a c, right? If we pick a c here, then this slope's the same, but it's not the same slope as that. You get it? Now, the proof is kind of interesting. Let's see. I'll show you what I do here. But what we're going to do is create a new function. Let me see if I can show you what I mean. The new function is, it's really kind of, I think it's very clever. Let's see if I can do something here. Hold on one second here. Yeah. Okay, let me go here. And anyway, let's say I'm going to connect another function that goes from here. Can you see it? In this case, f of a does equal f of b. You see that? So guess what? This guy, now how did I get this guy? Well, all I do is take my secant line, which we can call y. Yeah, we can call it y. Hold on. Let me try black. We can call this y equals f of x. And then that's the secant line. Well, let's just call it y is equal to the, let me do it like this better. Okay, and I say what I'm saying is that then I'll go back to here. So that, okay, so what we're trying to say is now is that if you notice that f of a, this is a here and this is b here, that with this green curve, that f of a, this is not, I don't want that, that f of a is equal to f of b. Oh, that takes us back down to Rolle's theorem, which we've proved or talked our way through. And the way we got the green theory is we take the secant, right, and we subtract it from here. That's how you get this point. And so this point subtracted from here, that's how you get this point. Subtracted from here, I'm subtracting them at different points. So that's what leaves that. So if I take that, and I'm left with this. And that is a kind of curve that we dealt with before with Rolle's theorem. So the first thing I have to do is come out with a secant, the equation of a secant of a line. I have this equation of the secant line. And first of all, I'm just going to solve generally for the equation of a line. And we know that this is nothing but the rise over the run, right? So I'm just saying that this is a particular y1 and an x1. I'm going to have 1 point, and then this is a general y and a general x somewhere. Okay, so now I'm going to multiply both sides by this quantity, you see, and let me go here. Okay, so I'm going to multiply by that quantity, so that's why this changes to this. So the slope times x minus x1 is equal to x, sorry, that's not x here, this is y, minus y1. Right, then I'm going to solve for y. So, so what I have here is I'm going to have a new function. So I'm going to solve for y right here, right? So now, if I decide that x01, I'm going to let it equal a. This will be x01, see it? Okay, so I know that x1 is the same as a. So now I'm going to distribute this m through to here, right? So that I have m times x. So that I have m times x, see it? And then I have m times a because x1 is a. And then it's going to be equal to, well, here it is, y minus 1. Now, the y value is f evaluated at a. Okay, so that's pretty cool. So now here I'll factor out the m, and I'll have this function of the line. Now I'm going to I'm going to subtract. Well, I'm going to say, okay, now y equals, okay, I got to there. So now I have this thing. Let me go over to here. So I'm going to have this new function where I'll take the f of x, that's the curve, the black curve, and I'm going to subtract the secant line. So this is a secant line here, and I'm going to subtract it from the curve. So what that's going to be equal to is that I got f of x minus y. But y, we already know that we got here, see it? What y is equal to. So in this y, I'll substitute this value here into this y, see it? And when I do so, then I have g of x is f of x minus the secant line. Now in this is actually, I'll put a y, but I'll put an s here so that we know that y is the secant, right? And it used to have like a y sub 1, but I changed this y sub 1. See it? It was y sub 1. But another, since I'm using the value of x at a, then f of a is the value of y. So now look what I have. I have f of x as the curve minus the tangent line. Now, the slope of the tangent line is the slope of the secant line, which is simply rise over the run. So I changed this m to this slope equation, evaluating at near the endpoints. Then you see I have x minus c, which I had it from here, x not c minus a, and then I have minus f of a. That comes from, because the minus is distributed from here to here, see it? And once it's distributed, now we can say that, let's test to see that both f of a and f of b is equal to 0, to see if it qualifies. So if I try to analyze g evaluated a, then everywhere where I have an x, I put an a. So I already have an a here, so it's like a constant. But here I'll put an a here, right? And here you have a minus a. You see, that's 0 already. So that takes all out. And then I have f of a right here, subtracts from here. And that gives me 0. Now let's try it evaluated at b. So everywhere where I had an x before, right here, I'll put a b. And then I have the b, see, and then I have f minus, this is just the slope, that's a constant number. And then I changed this x guy here. This remember this was x minus a. See it right here. So I put b in there, and then instead of having f of a, I have f of b. It's kind of hard to see my handwritings. I think it's genetic. Let me see if I clean that up a little bit. Okay, let's go here. Okay, so this is going to be minus. Hey, I don't want it that thick, do I? I'll put it right here. That'll be minus. Let's go here. It was f of x, but now it's f of b. Now let's see what happens here. Let me scroll up here, and so what happens is that, sure enough, g of b is equal to g of a, and that's equal to 0. So, going back and using Rolle's theorem, there must be a c somewhere such that the derivative of the function, there is some c such that the derivative of the prime is equal to 0. And that's how we solve for it. I don't know if that made life more confusing, or maybe you have to be stoned or have a beer. I don't know. Anyway, that's that.